The mean value theorem for differentiation is an important theorem that is going to be useful in proving even more important theorems later on, not the least of which being something called the fundamental theorem of calculus, which by its very name is obviously quite important to calculus in general. But for now, we just talk about the mean value theorem for differentiation. The mean value theorem is going to be based on, well, as the word mean implies, it's going to be based on connecting the average rate of change of a function to the actual derivative, the instantaneous rate of change of a function. Now, we already have the definition of the derivative as being the limit of the average rate of change, but this is taking a little bit of a different approach. First of all, let's start with a function that is continuous on a closed interval from a to b, and differentiable on the open interval from a to b. As we know, a function is not differentiable at an endpoint. So if we have a closed interval, the function is continuous and differentiable. So continuous meaning no jumps, no asymptotes, no holes. Differentiable meaning there's no abrupt changes of the rate of change of the function. There's no cusps or corners or vertical, or points where the function turns vertical, for an instance. So no vertical tangent lines either. So we have a function that is nice and smooth, no abrupt jerky changes or anything like that. In that case, there exists a value c somewhere on the interval from a to b, such that the value of the value of the instantaneous rate of change is the same as the value of the average rate of change over the whole interval, which, remember, is found by the slope formula. The total change in output value over the total change in input value. Now, this is, of course, very mathy. What does it actually mean? Well, remember what the average rate of change is. Let's consider this function here, which is f of x equals negative x squared plus 3x plus 4. And let's consider it on the interval from 0 to 4. That means that we're looking at this endpoint here at x equals 0, and this endpoint here at x equals 4. And the average rate of change is the slope of the secant line that connects these 2 points. So the slope of this line is the average rate of change on the interval from 0 to 4. Now, what we need to do is compare this to the derivative. If we look at the instantaneous rate of change, the instantaneous rate of change is the slope of the tangent line. Now, at the beginning of this interval, we're looking at a tangent line that has a very, very different slope from that of the secant line. The secant line is negatively sloped, but the tangent line is steeply positively sloped. Now, looking at it at the other endpoint, by the time we hit the end of the interval, the tangent line here is very steeply negatively sloped. Now, the idea of the function being continuous and differentiable means that the derivative, the value of the derivative, has to smoothly transition through all of the different points, through all of the different values. So if at this point we're looking at f prime being largely positive, and at this point f prime being largely negative, then it has to transition through all of the possible values between its large positive value at the beginning of the interval and its large negative value by the end of the interval. So somewhere in between, it has to hit this same slope as that of the secant line. Because if we look at the transition, as we go along, the tangent lines are going to get flatter and flatter until we hit our maximum value there. And then the tangent lines are going to start to become negative as we go along. And somewhere in here, there will be a point where the slope of the tangent line is the same as that of the secant line before going onward and becoming steeper again. That's the idea of an average. An average is supposed to take all of the values that are high and all the values that are low and find out where the middle is. So the idea is that if we start out with a value, again, if we start out with a value here that is at the beginning considerably larger than that of the secant line, and at the end finish out with something that is considerably smaller, or going from a large negative value to a large positive value to a large negative value, that somewhere along the line we have to have passed through the middle. We went from very, very large positive to very, very large negative, and somewhere in between we have to have passed through all of those middling values. And our job generally with this is to find what is the actual value of C where this occurs. So let's try this out. Let's actually look at this function for an example. We have here again, the function is f of x equals negative x squared plus 3x plus 4, and it is on the interval from 0 to 4. So we need a couple of things here. First of all, we do need to know what is the actual average rate of change from 0 to 4. Now we can get that visually. I chose a function that works pretty nicely visually, but we're still going to do the calculation. So we've got the average rate of change on 0 to 4 is equal to f of 4 minus f of 0 over 4 minus 0. And of course, we can substitute these x values into the function to get the y values, but we also have the graph right in front of us. F of 4 is 0. Meanwhile, f of 0 is 4. So what we get here is negative 4 over 4, and we get negative 1 for the average rate of change. Now, we also need the derivative function. So let's find that next. F prime of x is equal to negative 2x plus 3. That's easy enough to get by just using the power rule. Now, the idea is that, as the definition of the mean value theorem says, there is a point where the value of the derivative function is the same as the value of the average rate of change. So our job now is to set the two things equal to each other and say, well, when does it happen? What is the x value where the derivative is actually equal to the average rate of change? And again, this is easy enough to solve. We subtract 3 from both sides, and then divide both sides by 2, or by negative 2, excuse me, and we get at x equals 2. That means if we come up here to the graph and go to the point on the graph where x equals 2, the tangent line here has exactly the same slope as the secant line from 0 to 4. So our c value is 2. Now again, at some point we were steeper with a positive slope, and at some point we end up being steeper with a negative slope. So somewhere in between we have to have that slightly flatter and negatively sloped line that has the same exact slope as that of the secant line. And that, in a nutshell, is the mean value theorem for derivatives.